I built this using an open source project that can run for more than 2 years on a coin cell battery, and unlike most smart sensors that need new batteries every 6 to 9 months, this one barely uses any power. If you are also tired of changing batteries in your home automation project, or just love technology or want to build something similar, then this video is for you. I have put this project onto test, and we will check the 2+ years battery life claim, and we'll share all the results in this video. And I have got some ideas at the end of the video that I think could be first to market. Oh, and did I mention $0 for software, 0 for the cloud, 0 for the app, because it's all open source and that is the dream right there. So here was the problem and motivation behind this project. I have killed more plants than my falling hairs. At this point, it's like a superpower, but in the wrong direction. So I need something I could actually build myself, something that wouldn't judge me for forgetting to water things. So I thought, why not a plant health monitor? The plan was simple: grab an ESP32, call it a day. Right? Wrong. While scrolling through AliExpress at 2 a.m., because that's when all my best decisions happen, I found something wild: NRF 52840. Now, I know what you are thinking. Isn't that an overkill for a plant sensor? I'll say nope. Here's why it matters. It consumes about 5 times lower power consumption in sleep mode compared to an ESP32. So then I started looking at some sensors on ESP Home website because I know they are going to be comparatively easier to use, and then I stumble upon this project called b-parasite. And I'm not exaggerating when I say it's exactly what I needed. It's an open source project. It's got the NRF52 and it's already fully designed. Let me break down what this thing measures. And it's exactly what a plant actually cares about: temperature, humidity, light, and the MVP, which is soil moisture. So instead of guessing when to water, the sensor tells you. And again, here's the beautiful part: because it's an open source project, which means I could order the PCB directly from a website such as JLC PCB, which I did. Some components were out of stock, but that just meant a 20-minute hunt for drop-in replacements, which I'm putting in the description. So in case if you want to build it as well, you can just use the latest bill of material. So the PCBs finally arrived after a week or so, and the assembly was quite easy. Seriously, all I had to solder was the coin cell holder, and rest of the components I already opted to get them soldered from the JLC PCB itself. I also found some 3D printed designs for it on the printables website and ordered them through JLC PCB as well. Now I have put in the coin cell, and this is the time for the moment of truth. Will my J-Link actually talk to this NRF52 chip? So for that, I cloned the project, opened it in VS Code, and made the NRF52 and J-Link connections so that I can flash the firmware. And spoiler alert, it actually worked. So far the process was quite smooth, but now it was the time to test if it's going to work or not. So I opened the logs and they print for almost like 2 seconds, and after that it just stopped. I had no clue why it stopped and why it did not continue to print, and I'm sitting there like, after all this effort, did I really gamble on the wrong horse? After thinking for a bit, I realized the exact issue. The device was entering into the sleep mode on purpose. So actually, let me tell you, it's not an issue. It is the main feature. Because that's the whole point of getting 2+ years of battery life. The logs were designed to stop during sleep. So I commented out the sleep, enabled the debug logs, built, flashed, and checked logs again. And boom, there they are, printing every cycle like little digital soldiers doing their job. Pro tip: if you hate tinkering with VS Code, I have built and included a hex file in the description so that you can just pick it up and flash, and you are done. And you are welcome. Now, the next question is, how does my Raspberry Pi running Home Assistant even know this thing exists? And then there enters the BT Home or Bluetooth Home. So it's a standard format for advertising sensor data over BLE, which is Bluetooth Low Energy. And since Home Assistant now understands this format natively, boom, you'll have instant integration. I added to my dashboard and actually it looks pretty clean. Okay, so now let's do one quick test. Moisture is reading 0% in the air, which makes sense because there is no water contacting our sensor right now. So I dunked the sensor into the water and the reading came out, to my surprise, was 72%, not 100%, just 72. I felt personally attacked. Like, I give it a full swimming pool and it said meh, 7 out of 10. So I did what any reasonable engineer does at this point. I dove into the debug logs and turn out the firmware has a calibration curve baked in. Basically, it has a built-in idea of what bone dry and fully wet should look like in raw ADC numbers. And whoever set those values, they had a different board, different hardware, a different life. The firmware was expecting a raw value of around 157 for fully wet. My board in water reading 261. So the math was just wrong here. So I skipped the fancy quadratic voltage compensation. The firmware support looked too complicated to me and I just wanted to get it up and running quickly. So I thought it might be an overkill for this hardware. Constants probably could work fine for me. Two numbers for dry 540 and for wet 257. I put them into the firmware, built, flashed, opened the logs again, and then dunk it again into the water, and 100%. Physics is actually back. Okay, so now it's the time to check the claim everyone cares about. Can this thing actually run for 2+ years on a coin cell? So I grabbed a Nordic power profiler kit to measure the actual power consumption. So this power profiler kit can provide power to the sensor and then it can tell me how much power is consumed by my sensor in real time. So the sleep current came out to be around 3.5 microamps and active current came out to be around 650 microamps. When you run the math, this thing can realistically run for over 2 years on a coin cell. It's not a marketing number, it's actual measured math. But something weird I found out during sleep mode are these 12 microamp spikes about every 125 microseconds. Because if this is a bug, if it's something not implemented correctly, we could potentially push the battery life to over 4 years. Now, we can either stop here or take this project to the next level. Imagine getting notifications like water your snake plant now. And even better, moving this entire thing to matter over thread so it works with any smart home ecosystem. If that sounds interesting, let me know in the comments because that might be my next project. So that's it. If this kind of stuff interests you, smash that subscribe button and I'll see you in the next one.